should be at this standard. Today we're going to touch on a branch of numbers that you've not ever been exposed to. They're not scary, but they've actually existed all along. We just haven't had a need to learn them until now. This branch of numbers is called complex numbers. Not because we're trying to pull something out of thin air, but because they're numbers we cannot plot on a number line. Sometimes complex numbers are called imaginary numbers. They do serve a purpose. They wouldn't be part of our curriculum and part of our standards unless we needed them to solve problems as we move forward in the curriculum. But this will be the first time that you've seen them. These numbers allow us to continue working with a problem or solution when before we would have had to write no solution. An example of when these numbers would come into play is when you have something that looks like this. Now, if we had an equation that looks like x squared equals 4, to solve that, you might take the square root of both sides and you would say, okay, well, 2 or negative 2 could work, because if I plug in 2, 2 squared is 4, and if I plug in negative 2, negative 2 squared is 4. So both those would be solutions. However, here, when I take the square root of both sides, we would have to write, normally, we'd have to write no solution, because when I plug 2 in, like we might say, oh, that could be 2 or negative 2. But when I plug in 2, 2 squared is positive 4. When I plug in negative 2 squared is positive 4. There's no number that I can plug into this where I'm going to get a solution of negative 4. And that's because whenever you square something, if it's positive or negative, it's going to end up being positive at the end. So, imaginary numbers allow us to take an answer like this and actually write a solution instead of before writing no solution. So, normally we would have to answer this question with no solution, which is that circle with a line through it. But with complex numbers and its counterpart, imaginary numbers, we can now write an answer and be able to use it further. So the complex number structure, the term complex number is like the umbrella over all the types of numbers, like decimals, fractions, whole numbers, positives, negatives, all those types of numbers. This is like the umbrella. And then there's two branches. One branch, which is the branch that you have been working in all of your math career up to this point, are real numbers. And if we were to write them in a general form, we would write a plus 0I, meaning this is the part that we can actually plot. This is the imaginary part, because technically we could say every number has an imaginary part to it, but it's multiplied by 0, so it never shows up. Complex numbers also split off into an imaginary branch, and this has an imaginary number attached to it. Now, I know this isn't going to make much sense at this point until we actually look and define what a complex number is. We're going to actually do that next, define some of these terms. A complex number is a number that includes a real part and an imaginary part. A plus BI. And it can be A plus or minus. It doesn't have to always be A plus. An imaginary number, let me make sure. Yeah. An imaginary number is a number defined as the square root of negative 1. And we'll get more into that in a minute. But the square root of negative 1 is what the lowercase I, what it's going to be represented by. Now, this we do all the time. Like when I say pi, This is a symbol that represents a math concept, but we know pi is equal to 3.14. So whenever you see pi, that's just the symbol that tells you what number to put in place of it. In this case, this is another symbol I'm giving you, and whenever you see I, it's equal to the square root of -1. Going back up here, in this case here that we were talking about, we can split this number up into the square root of 4 times the square root of -1, because -4 is 4 times -1. And then when we solve it, we get plus or minus 2, because that's what we got when we took the square root of 4. But then the square root of -1 becomes an I. And so now we have a solution that we could actually use and plug in and check and all of that stuff, because now I have a symbol to represent this concept of taking a square root of a negative number. So that's what we're defining here. And a conjugate, when I say use the conjugate, that means to use the same expression, but change the middle sign. An example, if you have A plus BI, then the conjugate will be A minus BI. You just have the same exact expression, just change the sign in the middle. Now, this term we will get to when we divide complex numbers, because, again, our standard is adding, subtracting, multiplying, and dividing complex numbers. But the only time we use a conjugate is with the division, so we'll get to that. Go ahead and flip. Properties of imaginary numbers. There's two main properties. First main property is that I is equal to the square root of -1. So, you'll see in some of our answers that we have an I now, because we can do what we did over here, and instead of writing no solution, you can split up the values, and then that square root of -1 would become an I. So that's the first main property that we use when we're adding, subtracting, multiplying, dividing these. And then the next one is, in some cases, we're going to end up with an I squared. Now, if I was to square both sides here, squaring this side just knocks out the square root. And so actually, whenever you have an I squared, it changes it back to a number that we could plot in a number line. It changes it back to a real number. And so it's nice, and this is why imaginary numbers weren't invented, but they were defined. Because, like, I know my dad uses imaginary numbers when he does electrical work, because in those equations and problems they have to solve, imaginary numbers come up, but they can't just stop the process or stop the problem. So writing them as imaginary numbers instead of just saying no solution allows them to keep working with the values until they get to the end, and then stuff gets squared, and then they're able to change them back to real numbers. So this is a nice, it's nice that they were defined, because it allows us to solve problems that we were unable to continue with before. Now, adding, subtracting, multiplying, dividing, which is what you have to be able to do in Algebra 2 with these, are not hard, because you've actually already been doing all of the things that we need to do. For example, when you add and subtract complex numbers, you add and subtract like terms. We've been doing that all along. When you multiply complex numbers, we're going to end up FOILing, because complex numbers have that A plus BI, so they have two terms. When you divide by complex numbers, you multiply top and bottom by the conjugate. Which we haven't worked with conjugates, but really, it just is FOILing after that next step. Okay, so let's look at some examples. We're just going to do a and a B for example 1. Adding and subtracting complex numbers. So, if one complex number is 2 plus 3i, because a complex number just means you have a real part and an imaginary part. And then we want to add it to another complex number, let's say 5 minus 7i. If there's parentheses or there's no parentheses, this sign in the middle tells you what to do. So we're adding these together. We're just going to add like terms. So the like term with 2 is 5, so 2 plus 5 gives me 7. The like term with 3i is negative 7i, so 3 plus negative 7 gives you negative 4i. That's it. That's all you have to do. So when we subtract, let's say we're subtracting 4 minus 3i minus 2 plus 9i. Same kind of deal. We're subtracting. The sign in the middle tells us what to do with these. So we're going to subtract like terms. So the like term with 4 is 2. 4 minus 2 gives me 2. Like term with negative 3i is 9i, so negative 3i minus 9i gives me negative 12i. And you're done. Okay? It is that simple. You're just adding and subtracting like terms. Okay, go ahead and flip. Multiplying complex numbers. We're going to do an A and a B here. So if we did 2 minus 3i times 4 plus 6i. We have two binomials. So to simplify this, we would end up foiling, just like we would, well, we haven't really talked about foiling yet, but we've mentioned it. We might have even done it so far. But I know all of you have at least seen it before. So FOIL just gives you an acronym so that you remember to multiply everything together. F stands for first term, so we multiply 2 and 4 together to get 8. O stands for outer. So the outside terms are 2 and 6i. Multiplying those together get me 12i. Inner terms, negative 3 times 4 gives me negative 12i. Last terms, negative 3i times 6i gives me negative 18i squared because I have two i's there. Add like terms. Well, when I add like terms, those end up knocking each other out. And then negative 18i squared. Remember, one of the properties of imaginary numbers is that because of how it's defined, when I square it, it ends up turning back to a negative 1. So that means whenever you see an I squared, you have to treat that as a negative 1. So we're going to have negative 18 times negative 1. Well, negative 18 times negative 1 becomes positive 18, and 8 plus 18 is 26. Now, sometimes it'll work out when you multiply that you end up with just a number. But we're going to do one where that doesn't happen. So 4 plus I times 2 minus 3i. First terms give me 8 again. Outer terms give me negative 12i. Inner terms give me 2i. Last terms give me negative 3i squared. Okay, again, that I squared has to change to a negative 1. So we have 8, and then negative 12i plus 2i gives me negative 10i. And here I get negative 3 times negative 1. So this would change to a positive 3, and I can add that with the 8. So 8 plus 3 gives me 11. And there's my answer, 11 minus 10i. Okay. And then we're going to have some announcements here in just a minute. So I might use example 3 on Monday, but we're going to at least write it down. So 2 minus 3i. I really like that 2 minus 3i. Sorry. 2 minus 3i divided by 3 plus 5i. And then we'll do 4 plus 2i divided by 1 plus 3i. Oh, I'm going to make that 1 minus 3i. We're going to save B for Monday, but we are going to do this one together. If there needs to be pauses with announcements in a second, that's all right. Now, when you're dividing complex numbers, it's like a mathematical no-no to have an I in the bottom of a fraction. So to take care of it, we multiply by a fancy form of 1. And that fancy form of 1 has to be the conjugate. And you'll see why after we simplify it, because multiplying by the conjugate makes things cancel, and then we'll eventually make that I in the bottom disappear, which is nice. So our conjugate here is going to be the same thing as the denominator, just change the sign in the middle. Now, this is important. It has to be the denominator, and you can't have like 2 plus 3i in the bottom. It's not just flipping this and multiplying by it. It is the bottom, and you have to multiply by a fancy form of 1. So the top and the bottom of this fraction you're multiplying by has to be the same thing. Because we don't want to change the value of this, we just want to change the way that it looks. So multiplying by 1 doesn't change the value, it just makes it look different. Now, when I have fractions that I'm multiplying, we multiply across the top and bottom. So you'll notice when I multiply across the top, we're going to have to end up FOILing again. So let's go ahead and do that. 2 times 3 gives me 6. Outer terms give me negative 10i. Inner terms give me negative 9i. So negative 10 plus negative 9 give me negative 19. And then negative 3i times negative 5i gives me positive 15i squared. Okay, then on the bottom, 3 times 3 gives me 9. Outer gives me negative 15i. Inner gives me positive 15i. So negative 15i plus 15i, they're going to knock out each other. They're going to, well, let me rephrase that. They're going to knock each other out, which will always happen when you multiply by the conjugate. So negative 15i plus 15i knocks them out. 5i times negative 5i gives me negative 25i squared. Now, over here we have to keep simplifying because remember, whenever we see an I squared, that's equal to negative 1. So then we have 6 minus 19i plus 15 times negative 1. 9 minus 25 times negative 1. And then this becomes a negative 15, which I can then add with the 6. So negative 15 plus 6 gives me negative 9. Then on the bottom, this becomes a positive 25. So 9 plus 25 gives me 34. And now you'll notice on the bottom of our fraction, we no longer have any imaginary numbers, which makes it what we call proper form. And this would be like if you had to do a problem like this on a standardized test, this is how the answers would look. So that's why we have to be able to divide them. Okay, we're going to end there, which looks like it's actually perfect timing. And we're going to pick up with this on Monday as a review problem when we do whole group review. Have a great weekend.